Welcome to the first Hangout we have on air. Hopefully we'll have quite a few of these Hangouts there between now and your final exam coming up in May. The format for tonight is I'll be shortly screen sharing the problems which hopefully you downloaded from Edmodo. I'll just go through the problems with you. If you haven't tried them, you can watch them as they take place, or if you have done them and you want them corrected, you can check my solutions on the screen. So that's enough of me. I'm now going to switch to screen sharing, and hopefully we can start our questions, and you have those question sheets in front of you. The first picture you see there is the amazing picture of a bubble chamber. You can see all these nice round circles as the tracks of the particles make small circles and large circles. And from this picture we can determine which particles are which. And that's the kind of theme for tonight. We're going to be looking at how advanced higher physics looks at the electrons and their movement through electric fields and through B fields. So let's look at the first question then, and the first question on your revision tonight was this one here, and it's about a charged particle. There's a charged particle here, a charge Q, and is accelerated through an electric field with a potential difference V. Now we've come across that in higher before, and we know that the work done by the electric field on the particle W is just simply equal to QV. So there's nothing special about that, and we did talk about that earlier on today. But it's the second part which moves us into advanced higher. It says, treating the situation relativistically, and that's the clue, find an expression for the total energy of the charged particle. And the charged particle has rest mass m0. Well, we know then that the particle, first of all, has a rest energy, and the rest energy of the particle is simply given by the following expression. The rest energy is equal to the rest mass and then c squared. Now it's on top of that energy we're going to be adding in the energy gained by the electric field. So the total energy then is going to be equal to simply the rest energy m0 c squared plus what has been added by the work done on the electric field. And that's basically really the total energy. Of course, we can express the total energy in terms of mc squared, and that will equal to m0 c squared plus qv. So there we have an equation which we use relativistically for a charged particle moving through an electric field. Just before we move off this particular question, there's one point between the mass and the rest mass, and that's given by the equation m is equal to m0 divided by the square root of 1 minus v squared upon c squared. Now, when it comes to rearranging this formula to find the speed of the particle, if we know the mass, the relativistic mass, and the rest mass, then it becomes very difficult to change the v squared and c squared. Now, here's a little tip for you, which I hope will continue in your later problems. I'm going to rewrite that as m0 divided by the square root of 1 minus, I'm just going to say beta squared. And we'll know then that beta squared is equal to v squared divided by c squared. So really we've taken away this kind of ugly term here and replaced it by 1 minus beta squared. Now that'll make things a wee bit more easier for us when we go to rearrange that formula, because if we want to rearrange the formula, say m divided by m0, and that's going to be equal to 1 over the square root of 1 minus beta squared. See, it's a lot easier to rearrange it. And if I square both sides, square both sides and really turn them upside down, I would have m0 squared divided by m squared, and that would be equal to 1 minus beta squared. And therefore, I can now rearrange and have beta squared on its own, and that would be equal to simply 1 minus m0 squared all over m squared. So you can see that we can rearrange for this a lot easier by just making this particular expression, v squared upon c squared, equal to the b squared here. Makes things a lot easier for us. But the main part of this problem is that if we have an electric field and we have a charge moving through the electric field, the field will do work on the charge, but if we talk about it relativistically, we have to add on m naught c squared onto the work done by the field. So that's one particular equation you have to learn to explain and to understand. Okay, let's move on now to the second question for tonight, and it's very similar. It's an electric field, and these are two plates. One is at 100 volts and the other is at 0 volts. And the two plates are separated by a distance of about 0.01 meters. And here's a little electron here, and it's going to enter into the electric field here. So the first question is going to ask us, sketch a path of the electron through the plates. Well, we know that the electron as it moves into the electric field is going to experience an electric force, and the electric force F is going to equal to the charge on the electron times the E. So that's the first thing we want to do then. But we also know that a uniform electric field, this will be a uniform electric field. We also know the following. We know that the electric field E is also equal to the potential difference divided by the distance D across the two plates. So right away we can work out an expression for the force experienced by this little electron here as it enters into the region. So force would be equal to then simply Q times the electric field, which is going to be V divided by D. So that's us now got an expression for that. Force equals Q times potential difference over D. Now, the path of the electron then would be one where it would start to move up in a curve like that until it left the electric field area. So as long as it's in this area in here, it's going to experience that force applied to it, and the force is going to sweep it up like an arc or a parabola, to be more exact, from here all the way up to there. And the force it experiences is given by Q, the charge on the electron, times the potential difference, which in this case is going to be 100 volts, divided by the distance between the two plates, which is 0.01 meters. Now, how do we actually work out a distance if we're asked to find a distance between the electron coming in from the horizontal and coming up to E? How do we work out this particular distance here, which we'll call small y? How do we do that? Well, think again back to your higher days where you had a projectile motion. If this charge here is going to be subjected to an acceleration, then we can work that acceleration out, because acceleration is simply equal to the force divided by the mass of the electron. Now we already know what the force is. The force is QV over D, so for acceleration will be QV over MD. So we now have got an expression for the acceleration of that particle M. And at this point, if we want to find the displacement up the way, we resort back to our linear motion equations. Remember we had U, V, A, S and T. Well, in this particular case, the initial vertical velocity of the particle is 0, so it's just entering into the field. We don't know anything about the final velocity. We do know the acceleration now. It's going to be equal to QV over MD, so QV over MD. And but after the displacement upwards, so we have got U, V, A and S. So we can work out the displacement from that. S equals, well, sorry, we don't know V, so we wouldn't have to do that. So we'd have to find the time first. So as long as we know the speed of the particle coming in, which it gives us here, beg your pardon, we know the speed coming in, and we know the distance it's going to traverse, so we can work out a time. So in this particular case, we can work out the time. So we can work out the time. And we can work out time the electron is in the field, and that will be this value here. Therefore, all we have to do after that then, if I can just rub that part out, we don't know V at all, so we won't be able to use it. So we know the time the electron is going to move through the field, and therefore we know the acceleration as well. So we've got the acceleration, we've got the time, we know the initial vertical velocity is 0, and we want to find a displacement. We then work out the vertical displacement by simply saying S equals ut plus a half at squared. But since u is going to be equal to 0, the whole problem boils down to saying S equals 1/2 of the acceleration times the time squared. And we can work out that vertical distance displacement S, which we'll call y. So take a half, multiply it by the value of the acceleration you worked out, and then multiply it by the time it's spent in the electric field. So we know the speed it entered with, and we know the distance in the field, then we can work out time. I'll not do the whole problem to bore you, but that's the root of doing the problem. Here are the key points. The key points are as follows. In an electric field, an electron or a charged particle Q will experience a force F equals QE. But we also know that E equals V divided by D. The potential difference divided by the distance between the plates if it's a uniform electric field, which in this case it is. Put the two of them together, F equals QV over D. So now we've got the force. To find the upward acceleration of the charged particle, we just simply use acceleration equals force divided by the mass. And that turns out to be QVM over D. So we've got an expression for the acceleration. To find the vertical displacement, we have to do U vast, S and T. We haven't got the initial vertical velocity. We have, sorry, it's going to be 0. As it comes in, it's going to be 0. We don't know anything about the final vertical velocity here. We do know the acceleration because we've worked out an expression for it. We're after the displacement, and of course we know the T by just working out the speed of the particle and the distance in which the particle passed through the electric field. And by doing that, we can then use the equation S equals 1/2 at squared to get our vertical displacement. And that's our second problem done. Once again, I'll not do the full calculations for you. You can try the calculations themselves, and we'll see them next day in the class. So we've looked at the charged particle in two situations in an electric field. Let's now look at what happens when we have a charged particle which is going to enter into a magnetic field. And here's a little question here. It says a charged particle Q is going to enter into a magnetic field, and the magnetic field is into the page. Now, doing a hangout with the right hand was very, very difficult because you're not able to see my right hand unless I got on screen. But take it from me, the field is into the screen as you look at it. So what's going to happen to this charged particle as it enters into the magnetic field? Well, we know it's going to experience a force, and the force it experiences is going to be equal to the size of the charge times its speed times the size of the magnetic field B times sine of the angle between the speed and the magnetic field. In this case, it's 90 degrees. That's going this way, and the magnetic field is going into it, so it's 90 degrees. So the force the charge experiences is Q, V, B. That's the charge. So what will it entail? Well, it's going to mean that the first finger would be a field going in, the charge going up the way, and I think you can try it yourself. The force which experience would be along this direction here, and it's always going to experience a force in this particular direction, simply because the force must always be perpendicular. It must always be perpendicular to the field, excuse the writing, to the B field. So it's going to experience a force constantly pointing in towards the centre. So you're going to have a circular motion here. And when we have circular motion, we must have a centripetal force. And the centripetal force, Fc, we know is equal to mv squared, it's speed, divided by r. And in this particular case, that must be equal to the force experienced by the particle, qvb. Now, this is the basic ingredient for doing lots of problems with magnetic field and circular motion. Now, one of the questions you might get asked is, can you work out the radius of the orbit in this particular magnetic field? Well, we can, because we've got mv squared upon r equals qvb. So a little bit of cross multiplying, and we have the following: v squared equals qvbr. Two v's, one v will cancel from here, one v will cancel from here, and you're left with mv equals qbr. And therefore, we just rearrange, you get m times v divided by qb is going to equal to the radius of the orbit. Now, this is a standard proof, and it comes into the advanced physics with the magnetic fields and charged particles quite a lot. So we know then that the radius of orbit is the mass times the speed divided by q over b. So you can see for fast-moving particles, you're going to have a big V, therefore you're going to have a big kind of radius of orbit. So that's a very important little expression to learn. And it all stems from knowing to set the magnetic force equal to the centripetal force. So practice that proof and get to know how to work out the radius of a charged particle as it moves through a magnetic field. And in fact, that was the picture we had at the very beginning with all those nice, beautiful circles of the particles in the cloudy chamber. So that finishes up question number 3 for us. So we're doing quite well. Move on now to our next question. It's something which we haven't done much revision on, but it's a very common one, because it's putting the force acting on a current carrying conductor to practical uses. And here's one here. We have a coil of wire. There's a coil of wire here. It's just a simple rectangular coil of wire. It looks a bit like it's floating in space at the moment, but to make the diagram simpler, this is the axis of rotation, this dotted line here. And the coil has got a length L, and it's got this kind of breadth small b here. There's a magnetic field between the two faces of this magnet here, and we'll call the magnetic field capital B, the magnetic field there, like that. Now, what happens to this part of the current carrying conductor when it's in the magnetic field? Now, you have to know, because of the diagram, the current is going into the page here, just slightly elevated to make us see the loop or the rectangular coil. So the force experienced by this part of the conductor here, and we know that from our equation, force equals the current in the loop, current into the page, times the length of the conductor, times b, times sine theta. That's one of the standard equations. And that is the equation of the force acting on a current carrying conductor of length L in a magnetic field B at a certain angle. Now we know, because the current is going into the page and the magnetic field is going across the way here, north to south, then sine theta will be sine 90, which is going to give you 1. So the force experienced by that part of the coil is I times the length of the coil, L, times B. So we're going to have a force which is going to be pointing up the way like that, pulling the coil up. And likewise, when the current moves round and comes down to this position here, because of symmetry, you're going to have the same force pulling down like that. So there's the two forces just worked out, force there, and the two forces are exactly the same, pulling it down. Now, it's asking us here for an expression for the total torque acting on the coil. Remember what the torque is? The torque is equal to the force times the distance r from the center point. So in this particular case then, we've got two identical forces pulling down. So in this particular case, we have a total torque. We can say a total torque, if I can write it that way, of equal to 2 times the force times the distance r from the centre. Now we know the value of the force acting on the conductor, and we know the value of r. R is just simply b divided by 2. So the total torque acting on that single coil is going to be 2 times the current I times the length of the conductor times the magnetic field B times R, and R is going to be small b divided by 2. So if we can write that again as a total torque total equals 2 times b divided by 2 is just simply b. So we've got I L B times small b. Now here comes a smart move here, which we really have to have our wits about, is the area of that coil. If we just worked out the imagined area of it, would be simply equal to the length times the breadth. So it would be length times the breadth for the area of that coil. And you can see down here we've got the length here, if I can highlight this for you. We have got the length of the coil, and we've got the breadth of the coil. So that equals the area of the coil. So right away we can rearrange that formula to give us that the total torque acting on that little coil is going to be equal to the current flowing into the coil times the magnetic field B, which is in the magnetic inductance, times the area of the coil. So there is a total torque acting on that, which is going to spin around in that particular direction. Now, if we have more than one coil here, then we can actually say that we have a bigger torque, and that would be simply equal to, if we maybe say n coils here, 1 more coil, 2 more coils, 3 more coils, 4 more coils, then we'd just simply say that the total torque acting would be n, being number of coil turns, times I times B times A. So if we know the current going in here, and we know the magnetic field strength, we know the area of the coil, we can work out the torque which is applied to it. And remember, when the coil, the loop starts to move up the way, you're going to get this particular situation here like that. There's the loop. There is the force acting on the two ends of the coil. You can see the angle between them is becoming bigger. It's bigger from the central point, the pivot point. Therefore, the torque is going to sort of become smaller. So when you lose torque, and we know the cure for that becomes smaller. We know that when we have two plane magnets here like that, this is the situation where you get. So to make the torque constant, we would just exchange those two magnets there for two semicircular magnets. So at any particular time, the torque would remain actually constant, and that you'd have a better motor. Now learn that proof and be able to put in the numbers for it to work out the total torque acting on that loop, which makes up an electric motor. Well, we're doing quite well. We have only one question to go, and that's the question we had in the class today, which we looked at, and it's a very famous one. So we're now leaving the realm of electromagnetics and going back to Unit 1. And we have this situation here, which is quite famous. It's been asked quite a lot now in Advanced Higher, so we have to be really ready for questions like this. And it looks complicated to start with, but all we've got to know is that this particular loops of wire, when the 1 kilogram mass begins to fall, you're going to unwind, and you're going to have the mass falling. So the first question is very straightforward. It says, find the average angular acceleration of the cylinder. Now don't worry when you see the word average angular acceleration, because in this particular case it will be changing slightly as the mass falls. So always rely on your u-vast equivalent of rotational motion. We start off with the initial angular velocity the final angular velocity, the displacement goes through, the angular acceleration, and the time taken. So in this particular case, just fill in everything you know. We know it's going to go from rest, 0. We know the final angular velocity is going to be 20 radians per second. And we know the angle which is going to go through is 5 revolutions. So 5 revolutions is 5 times 2 pi. Remember, 2 pi is 1 revolution. So 2 pi radians equals 1 revolution. That's something we have to know. So if you go through 5 of them, it's going to be 10 pi. And you can work that out yourself to get an answer for that. And this is what we're after, the angular acceleration. We don't know anything about the time in this particular case. So we've got omega naughts, we've got omega, we've got alpha, we've got theta, the angular displacement, and we've got the angular acceleration to find. And just think of the linear equivalent of that, and I would go check the data book, and that's the one which you would go for, plus 2 alpha theta. So the angular acceleration alpha is a straightforward case of doing omega squared minus omega naught squared divided by 2 times the angular displacement. So if I put all the numbers into that, then I should get, in this particular case, alpha, you can maybe try it out yourself later on, correct me if I'm wrong, you get 6.7 radians per second per second. We've now got the angular acceleration. The next part of the question would say, what is the distance the 1 kilogram mass falls? Well, this is the one we did in the class today then. If it turns around 5 revolutions, so we've got 5 revolutions, we're going to unwrap 5 revolutions of string. It's going to be unwrapped. And we know that for a revolution, that means 5 circumferences. So that equals 5 times the circumference 2 pi r, which in this case will be 5 times 2 times pi times the radius of the actual cylinder, which is 0.2 meters. So therefore we can find the distance gone quite easily, and the distance gone, and work that out, should be something like 2 pi or 6.3 meters. So that's how you'd work out the distance which the rock would fall. Now, one of the other questions here is a very famous one. It's find the speed of the 1 kilogram mass at this particular time. Well, to find the speed, this totally confuses people because they're so wrapped up in the speed of the particle, so wrapped up with it, then what happens is that they can't remember how to work out the speed at that particular point. Well, if we know the angular velocity at that particular point, which we've just been told is going to be 20 radians per second, 20 radians per second, then if we use the relationship, which we often maybe forget, V equals omega r, we know the speed at that particular point. So we can work that out, and we can find that itself is 20 radians per second times the radius, 0.2. So we're going to get a speed of 4 meters per second there. So that's the 2 ways how to do that. That's the way how to work out the distance it falls and the speed at that particular point. So we're going to be moving at 4 meters per second at that particular point there. But bear in mind, it's falling a certain distance. Now, as it falls a certain distance, it's going to change its potential energy. And that potential energy will be changed into not just simply kinetic energy, but it'll be changed into rotational energy as well. So the total energy, you can work out the energy loss by working out EP equals mgh. But you've also got to remember that the total energy is actually equal to the kinetic energy, half mv squared, plus the rotational kinetic energy, which is a half I omega squared. So as far as this problem goes, I'm not going to roll it for you. You can try it yourself. We can work out the loss in potential energy by doing mass times gravity times the height it dropped. We now know we can work out the kinetic energy, and if we know the angular velocity at that particular time, omega squared, then you can see we can easily work out the moment of inertia of this particular cylinder here. And that's how we do work out the moment inertia of things. We can drop masses and find the velocity of them, and then compare them with the potential energy lost, and then we can rearrange this to get the equation for the moment of inertia. Now that's us done a half an hour of tuition. I hope that has helped you a little bit. We hope to plan to do this in the next couple of weeks, right up to, in fact, Easter time. I hope to be doing maybe one every week, and the question will get a wee bit kind of harder. We have got the prelim on our mind at the moment, so I hope that's going to help with the prelim, because take it from me, some of the questions, well, all the questions tonight which we've done will appear in the prelim in some form. So you can play the video back, you can go into YouTube and you can get the video from there as well, a link to it. I'll give the link on Edmodo, and you can sit back at your leisure and study the questions which have been done. I hope this hangout's been a great help to you. I hope it's the first in the series between now and we go towards the big final exam. So from me at the moment then, Mr. Mallon, thanks for listening to me, and thanks for putting up with me for this half hour, and hope to see you back in class on Thursday, and maybe another hangout again next Tuesday. Bye for now.